Good evening. Friday, May 19th, 2023. Been reading about the differential equations and theorems in the integral equations for the plane curves, and conversely, the differential equations and their solutions, which in planes are plane curves. And here it's been framed in a particular region, only the first quadrant. Positive numbers in x and positive numbers in y. And similarly to how the origin is the center of things, here it's framed in a sort of notion that's about reflective about the identity x equals y and y equals x. And that is a kind of milieu and a constraint in the singularity, for these singularities being those things that go to indeterminate forms yet still have analytical character, right? 0 over 0, infinity over infinity, and such things. Or in terms of differentials, whether they vanish or not, as they're maintained in their square, in terms of the usual notion of the differential in the quadrature, or in the polar coordinates, when you have a differential in the angle and a differential in the radius, these kinds of things. That this idea of this semi-dimensional x and y, then reflecting about the dimension being in the identity function, calling this the identity dimension, then gets into, for example, 1 over x, or the reciprocal function, the inverse function, or reciprocal, where an inverse and reciprocal are usually refer to the same things, but reciprocal is just that much stronger, just kind of reflecting the orthogonality, again, of things. The things cross at right angles, or in their transformations, they preserve angles, those conformal mappings, preserving the legs of vectors or preserving angles in the tensorial products and these kinds of things. That it's been interesting for me to kind of just think about that, because I've never really seen an approach particularly in this manner, because the general approach is already way after the whole application of the linear curriculum. The linear curriculum must build on itself. And so by the time it gets to higher in the curriculum, there's not necessarily the time to make a deconstructive account, provide the context of intuition, for instinct and intuition, for the constructivism that needs to see definition, to see derivation result. That the arithmetic is deconstructed, here too addition and division, that the algebra is deconstructed as about quantities besides symbols and variables, that the topology is deconstructed as about various topologies, which are under definitions of what is a topology, that continuity is deconstructed to make for at least 3 definitions of continuity, this line continuity, field continuity, and signal continuity. And geometry to, if not really deconstructing geometry, having though this idea of a non-standard continuum kind of founding what results, that Euclid's axioms are derived from otherwise the existence of a point in space, instead of being defined as primitives and elementary objects and objects of that theory, to make it for, and then the number theory is applied, is about the integers and the reals, and whether the reals follow from the integers or the integers follow from the reals, and vice versa, in terms of what are the rationals and irrationals. And here, when in the first quadrant there are only positive numbers, it's a ray, if not quite a full dimension, it's a ray. And these kinds of things, with respect to, though, that difference exists on it, with magnitudes and differences in magnitudes. For them, that these complementary duals that make so for a deconstructive account, that it's possible to arrive at a richer and fuller context for intuition and instinct. That is not necessarily what would be a product of the linear curriculum, which is basically requires that, because it can only be assumed that the model instructor and the model instructee result, that all that can be assumed to be defined and derived is what's relayed from the instructor to the instructee, and thus that it results that accordingly to design a curriculum that enables the student to have success understanding mathematics and its applications and having exercised it, that it requires following a course that these definitions accumulate. And so everybody already has the entire kind of milieu of arithmetic all together, algebra all together, pretty much, and such things as a topology chosen and a definition of continuity or completeness chosen for field continuity, and least upper bound and property in measure 1.0, which enables the implementation of the fundamental theorems of calculus. That these sort of things then in this richer and fuller context, which is still all objects of mathematics, all these theories of elements of objects of mathematics form just one theory. It's mathematics together. That there's a logic and it's the logic, and that there's a mathematics and the mathematics and dot dot dot. For the fundamental physics, that there's a physics and the physics, where the challenge is to find what universal laws of nature apply that make for fundamental elementary physics. And there as well, the deconstructive account is applied. That here in Imre Lakatos's book, one of the chapters is on Cauchy on the principle of continuity. And so I made mistakes of my own. I haven't already read these works, and so I'm just kind of examining them. And he talks about Fourier's memoir sur la propagation de la chaleur, which we've been reading about in the Fourier analysis and boundary value problems. It was Cauchy who gave the first proof of this conjecture that the limit of any convergent series of continuous functions is itself continuous. I think it's pretty clear that if a convergent series defines a real number and it has a limit, then it's essentially having the least upper bound property, the series for any of its initial segments, and thus that it arrives at, for any m, there exists sufficiently larger n such that the difference between fm and fn goes to 0, and the difference between the difference between fn and the limit goes to 0. That when the continuous function is defined by any topology, for example, the usual default open topology, and there are others, that it's pretty easy. We find the conjecture in his proof in Cauchy's celebrated 1821. Of course, such methods of exhaustion and their proofs are familiar since antiquity, but the notion that we can deal with infinite series, and this was before even infinite series could be considered numbers until their convergence was established, and there's various tests of convergence, and some identities do not meet all tests of otherwise convergence, so there's some pseudo convergence or pseudo tests, in a sense, for those which are absolutely categorical and biconditional and if and only if. Because something like Stirling's approximation for n factorial is not convergent to being any different from n factorial, but it's convergent in a sense. That's not a lot of the realm of development in terms of convergence and for example this convergence between something like Stirling's form for n factorial over n being equal to 1, converging. So that makes a milieu where the infinite series were kind of well defined, and that their arithmetic then gets into what's like the telescoping. And so the telescoping is otherwise that you can find any way to rearrange terms in an infinite series to just put the big ones in front and the little ones behind, and maybe it would look like it would converge, or vice versa. You can't always rearrange the terms, and it kind of really depends then what you're measuring it against. And so there's a lot of establishments then of the The well-known expansions, I guess you call them, like Wallace's theorem for pi, and the exponential function x plus 1 over x to infinity, that make for the convergence series is a great thing. And then there's the notion of the equivalence classes of the sequence that are Cauchy, that have the Cauchy criterion, are a definition fairly enough of real numbers, where Deduction cuts just will not do. What if you just partition the rationals above and below that? Then you could say that they're all the real numbers. It's like, yeah, if you partition them above and below by the real numbers, but otherwise it will not do. That otherwise something like the line continuities, iota values, real numbers. Between 0 and 1, there's extent, density, completeness, and measure. In sigma algebras, providing measure for completeness provided by least upper bound being trivially implemented by the next, which is kind of nice. And extent and density for a continuous domain, that's defined on the unit interval, the continuous domain of unit interval by iota values. But then, so Imre Lakatos here is talking about Fourier and Cauchy and about proofs and refutations. And so he has here a list of, there's a simple pattern of mathematical discovery, or the growth of informal mathematical theories. It consists of the following stages. 1, primitive conjecture. Now this primitive conjecture could be kind of, you can read that in a couple different ways. As a conjecture that is primitive, meaning it's not very well defined as a conjecture, or it's a conjecture in the primitive elements. Well, what is a fundamental theory, a fundamental elementary theory? Well, the elements are fundamental, and it's expected that all things are built from them. They're very simple, like the atomic building blocks or the building blocks. And, well, what happens when we already have, like, our Legos, and we also have a board that we can put them on with Lego pegs. So you have, like, the space of Lego pegs with Legos upon them. Those are two different kinds of building blocks as an example of necessary disambiguation of the space and the thing with regards to putting those together. Where traditionally the Lego base has no pegs or holes on the bottom side, it's just pegs. So a primitive conjecture, or Lakatos's first stage of growth, can be read as a variety of things. Here, for example, it also discusses the idea fix, or whatever's like, I have this part of the theory, and so whatever else I find, I'm fitting to it. So if it doesn't fit, then the conjecture is done. And if it does, then it must be because other things are held as particulars or constraints to make it so that we can work out how, for example, this middle of nowhere approach makes for the arrival of the analysis when the inductive analysis attains to, it reaches out to infinity, and that something from infinity attains to comes down to 0. What's in the middle? Or from negative infinity to infinity, 0 is in the middle. How does it get there? Middle of nowhere. This is the result of the deductive analysis, that otherwise the inductive impasse fails. So this is the realm for the dialectic instead of this one-dimensional thinking, as Mark Hughes puts it. I just got a book by Mark Hughes called The One-Dimensional Man. And so it's kind of postmodern, and he kind of, it's a social account, and it kind of lays into and criticizes the risk to the individual. But it can well be read as everybody needs to have their own critical thinking. So anyways, Imre Lakatos goes on with his next stage. Step 2, proof, a rough thought experiment or argument decomposing the primitive conjecture into sub-conjectures or lemmas. 3, global counterexamples. Counterexamples to the primitive conjecture emerge. 4, proof re-examined. The guilty lemma to which the global counterexample is a local counterexample is spotted. So this is where you find things that are undecidable or undeciding, so they can have multiple models if the rest of their axioms or rules or fundamental theorems are independent. And so that gets into whether there's a standard model of integers. Well, what if one's a fragment and one's got infinity? or infinite? What if one's infinite, one's extraordinary infinite, for example? Or what if there's not division by zero, or what if there is? Or what if there are only positive numbers, or they're positive and negative numbers? Just to establish something that for some would have as simple and clear, and others will have as not. These different features of the richness of arithmetic and algebra usually is kind of fully assembled and put together and set down for people. And geometry too, if you count the just defining points and lines and planes and dot dot dot, but never really defining the infinite Euclidean space, is kind of the same thing as having a point in the space, and it happens to be each one of those things, dot dot dot. That these are kinds of just examples about these counterexamples and multiple forms, multiplicities, duals, and all these things. The guilty lemma may have previously remained hidden or may have been misidentified. So Lakatos is expressing that no, not all efforts to find things in mathematics work out. People give up, there is no answer, they determine that there is no answer, or they determine that they don't have enough time to determine that they give an answer, or they find that something was assumed, and so whether or not it was independent or not was not established. There's many modes of correctness and incorrectness. There's the howler, which the howler is something just so arbitrary, egregiously wrong that's applied that when it comes out, it's like, oh, well, now I can see why all your theories are wrong, because every single one of them, you just carried on what you thought was correct, which half of them were, with this howler, but it's not so. And then there's the establishment of things. First, you find that there's grounds for definition, there's room for definition, there is possibility to over-define something or under-define something. These deconstructive accounts are as well kind of overarching accounts when they're reconstructive to be, explanatory and not just dismissive. The theorem, the improved conjecture, supersedes the primitive conjecture with the new proof-generated concept as its paramount new feature. And so Emery Lakatos's theory of discovery is, again, subject to its own deconstructive account. He says, these four stages constitute the essential kernel of proof analysis, but there are some further standard stages which frequently occur. 5. Proofs of other theorems are examined to see if the newly found lemma or the new proof-generated concept occurs in them. This concept may be found lying at crossroads of different proofs and thus emerge as of basic importance. And so here it brings to mind the transfer principle and these bridge results, or the ponts, and the idea of, after a deconstructivist count, re-examining what went into the development and the derivations to see where it would change to make it so like so. It's kind of like in mathematics today. It's like, well, let's build all the standard linear curriculum. It's like, well, we need something that fills the Jordan measure, like the iota values. And it's kind of like a completely metrizing ultrafilter, like either the signal reals or the line reals, but it's got to be above. So let's build them way, 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 way above. Or let's take ZFC, the normal axiomatic set theory for normal descriptive set theory, for all accounts of foundations of the ordinary and the usual linear curriculum, and that's the status quo, it's standard. Well, by the time I got all done with that, let's add an axiom like univalency, which means you can take infinite unions, and it's otherwise just kind of like, well, whenever I want to, I'm just going to invoke univalency and make a completed whole of things, even though if that would have been present in ZOC, you could have derived inconsistencies, and putting them together with them without establishing why and where there are and aren't bridge results is hypocritical and considered unconscientious, unmathematical in a sense, illogical. Let's just say that. And so, for example, when these kinds of things are seen to exist, because the theory's got to make room to accommodate, otherwise these things that would be like, there's a glaring hole in your theory about these objects otherwise. So this is then what he calls these newly found lemmas, this concept may be found lying at crossroads of different proofs and thus emerge as of basic importance. So similarly, when we go through something like a physical derivation and say, hey, you know, what happened in our physical derivation, we made all this stuff and came forward as of about conservation laws. It's like, well, I got a brand new rule and it said I have to re-implement everything as conservation laws as continuity laws. Well, then that sees a revisiting of the whole thing. You got to revisit the derivation to your new rules still have to work with the old rules. The old rules cannot be broken by new mathematics. The new, except with regards, you can show a theory is inconsistent, but for the parts that are existent and are consistent, it's necessary for a new derivation, a novel derivation, to offer apologetics and both defend the existing mathematics and build a new one. Otherwise, it's just an exercise in proving some counterexample and extended, not an example of actually integrating new mathematics into the curriculum, into the understanding, into the knowledge of the mathematics, into the mathematics. So this is an example then, after you found something, then you start relating it to other facts. 6, the hitherto accepted consequences of the original and now refuted conjecture are checked. Checked. So the hitherto accepted consequences of the original and now refuted conjecture are checked. This kind of speaks to what was just mentioned about it, as there needs to be the revisiting and the derivation, thus that it's built, the outsides of it that fit together. 7, counterexamples are turned into new examples. New fields of inquiry open up. And this basically expresses where sometimes this is going to be on the inside and sometimes it's going to be on the outside. For example, when you only have positive numbers and then you define negative numbers, it opens up in that way. But it closes things to do that work that the only real roots are also positive real roots. So here in this example, this deconstructive account of the identity space, the identity dimension, x equals y, as an example of basically it's like, what's this theory in the E-day fix about? Well, it's about 0 and what happens when you divide about it. You know, in terms of that, otherwise it is or isn't placed in all the equations at all, wherever algebra would make it so, at all. And it is, that it's placed in all these differential accounts where quantities are vanishing. It's among the indeterminate forms in those theories, how as it was like so. So when we say new fields of the inquiry open up, they either totally expand comprehension, or they provide for that it requires a deconstructed account that has expanding comprehension in a different way. And either way, new fields of inquiry open up. So then Lacto says, I should now like to consider another case study. Here the primitive conjecture is that the limit of any convergent series of continuous functions is itself continuous. It was Cauchy who gave the first proof of this conjecture, whose truth had been taken for granted, assumed therefore not to be in need of any proof throughout the 18th century. It was regarded as the special case of the axiom according to which what is true up to the limit is true at the limit. Finally, conjecture's proof in Cauchy celebrated 1821. Given that this conjecture had hitherto been regarded as trivial or true, why did Cauchy feel the need to prove it? Had someone criticized the conjecture? Here, basically, everything has to come from foundations, which, for example, is axiomatic set theory, and there's nothing that's not proved. There can be no statements mathematical that are not proved. If a mathematical statement sans proof, it's called a conjecture. But otherwise, it's not so established that such a thing is true or false, only that it hasn't been proven true or false. Whereas though conjectures that are proven are simply called proofs, and their conjectures were so. that counterexamples to the Cauchy conjecture have been provided by Fourier's work. Fourier's memoirs of the propagation of the Chatelier actually contain an example of what, according to present notions, is a convergent series of continuous functions which tends to a Cauchy discontinuous function, namely cosine x minus 1/3 cosine 3x plus 1/5 cosine 5x minus plus dot 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 1 over 2n plus 1 cosine 1 over 2n plus 1 x. Now, this is where we have more modern definitions of convergence, as were mentioned, where something like sine x over x goes to it has a limit. It's convergent, even though it goes above and below its limit infinitely many times. It's not that the next, or according to a case for induction, that n for any n, that n plus 1 is closer to the limit, and that in the limit that the distance between n and the limit goes to 0, but that there exists a sufficiently larger n, thus that there exists a sufficiently closer value to the limit, and for any given value there exists only slightly larger m than it that is not farther away. So it shrinks its bounds, say. So this isn't so much a counterexample to Cauchy's criterion as an example of the failure or ill-posed nature of a convergence result, which for some would be like, that's just doesn't need a proof. It's just as simple as that. It's a three-liner. It's so. You can build a case for induction in it recursively that makes it so. So these are the kind, but here is this lactose example. It's just to make clear that would be required to carry it out. Sure, still, but closed definitions like so, as was talked about here, the definition of functions versus continuous functions, and Descartes' functions versus functions that include non-Cartesian functions. These are kinds of things that get into definitions of the elementary objects of each of these different theories, because then things like the objects of geometry, the objects of number theory, sets and parts, and the objects of arithmetic and objects of algebra can each be picked up a piece according to the functions among them and the topology of those and the continuous about operators that then can be treated like so. So when convergence is first class and primary, then if there's any counterexamples at all, then it's not. And instead it's arbitrarily not independent from other supporting axioms or theorems, where theorems suffice. Fourier's words about the perpendiculars in the graph are telling. He considered these limit functions to be in some sense continuous. In fact, Fourier certainly regarded anything as a continuous function if its graph could be drawn with a pencil, which is not lifted from the paper. Thus, Fourier would not have regarded himself as having constructed counterexamples to Cauchy's continuity axiom. This is in the definition of functions. It was only in light of Cauchy's subsequent characterization of continuity that the limit functions in some of Fourier's series can be regarded as discontinuous, and thus that the series themselves can be seen as counterexamples of Cauchy's conjecture. So what we can basically frame this is that for the French and Cauchy, and then later into more so Bourbaki and the Langlands program in algebraic geometry, and them having settled and abandoned any notion of a deconstructivist count, maybe because it was too obvious to them that there was none, but really it's a fallacy to think there isn't. That then those things would have been settled and decided, and that's so, that can be a complete theory, but it's also a consistent theory, but it's also an incomplete theory. And the definitions thereof are not so, for otherwise the objects about these other parts of the theory that are free, as about the otherwise interpretations besides these ones, that Fourier's innocent continuous drawings seem to become wicked counterexamples to the old long established continuity principle, that's wrong. That seems that, oh, what's the word, that it had been appropriated inappropriately. Cauchy's definition certainly translated the homely concepts of continuity into arithmetical language, such a way that ordinary common sense could only be shocked. What sort of continuity is it that implies that if we rotate the graph of a continuous function of a little, it turns into a discontinuous one? See, that's the problem, because it's not even a function anymore, according to him. And that's similar with this, algebraic geometry, or differential geometry, if you excuse me, these submersions and sheaves. They say, hey, we're going to have a great series and lecture on all kinds of wonderful methods in differential functions, but we're going to restrict ourselves to functions where their differential derivative is neither zero nor infinity. Not infinity, which many of these continuous functions or differentiable functions are assumed to be, but not zero either. That is to be called out, and it's explaining why such idea of this descriptive differential dynamics is also dynamics in definition. And so then when you look to attach any of all the following theorems or whatever, and what's called a function somewhere is not a function somewhere else, or there's properties of it that don't apply, do and don't apply, that it needs to be disambiguated in terms of the intentionality and then extensionality. And therefore what is still contained, what is not still contained, or vice versa, what is expanded and not expanded, is still as that still hold true. And so if it doesn't, then that's vagary or ambiguity or the existence of independent hypotheses or conjectures of the otherwise objects of said theory. And so when that's applied then to the whole totality of the foundations, it has to work out that there are no logical paradoxes at all, and that the theory is quite grandiose, yet still in a sense totally elementary, about the fundamental primary elements of the objects of mathematics, and then how that's numbers for counting or points for spaces, these kinds of things. To have a sensible, fungible, and tractable mathematics that for the mathematically conscientious mathematician is a rigorous formalism and well-defined. So when we're looking at these different subfields of differential analysis, like the submersions and the symmetries and the sheaves of topology, about these particular restrictions of these submersions, the particular different kinds of topologies for these sheaves, for the particular milieu of symmetries and these symmetries, in the subfield of the entire plane curve and their integral functions vis-a-vis and versus the differential functions and equations and their solutions, as complementary duals, that this is relevant to otherwise what would be big problems with trying to relate the same objects, otherwise unqualifiedly, from one of these subfields to another. They need these bridges, these ponts or points between them, and the extensionality for the intentionality to sort results to disambiguate what otherwise reflect quantifier dilemmas or false inferences, and that for some would have ex falso quodlibet, but here is ex falso nihilum, and especially when you get finally to it, that you can have a foundation that is not ultimately irresistant to meddling. Cauchy must have Fourier's series seemed to work, and when Abel, in 1826, 5 years after the publication of Cauchy's proof, mentioned in a footnote of his that there are exceptions to Cauchy's theorem, this constituted a rather intriguing double victory. Fourier's series were accepted, but so was Cauchy's startling definition of continuity and the theorem he had proved using it. Except there are exceptions to it? No, for some that's immediately, that means it's like, sorry, it's not the rule anymore. it's an exception itself, and that there are exceptions to it, or other exceptions, and the rule is that there are exceptions, for example. And otherwise, what we have is a strictly regular. And Cauchy's proof of the biconditional and necessarily and if and only if being at all false makes it entirely false. And so that seems a double victory for this program, but not for mathematics necessarily. But it does make it simple to keep it in the linear curriculum, but it seems not conscientious. You know, it does not seem, it seems hypocritical, and it is. It was precisely in view of this double victory that it now seemed that there must be exceptions to the specific version of the principle of continuity we are considering, even though Cauchy had flawlessly proved it. Well, he hadn't sufficiently deconstructed his account. He's basically ignorant, and he assumed, and then the traditional saying about assume is that the word assume is split into the words ass and you and me, and that ass is a donkey and considered a stubborn and foolish creature, and one that is the butt of jokes. And so when you assume, you make an ass out of you and me both. And so it's considered a bad idea to take axioms without critical examination thereof. If you don't know your beliefs, you don't know what you believe. So those are the kinds of things that get into why Imre Lakatos is coming across as kind of an apologetics for this hypocritical, non-conscientious carrying on of what's otherwise a body of developments that go together in a linear curriculum. Cauchy must have reached the same conclusion as Abel from the same year he gave, without of course giving up his characterization of continuity, a proof of the convergence of the Fourier series. He must have been very ill at ease with the situation, however. The second volume of the Cours d'Analyse was never published. What? I wonder what's in it. And, which is still more suspicious, he produced no further editions of the first volume, allowing his pupil Moigno, when the pressure for a textbook had become too great, to publish his notes of his lectures. Given that Fourier's examples were now interpreted as counterexamples, the puzzle was evident. How could a proved theorem be false or suffer exceptions? Well, there's vagaries in definition. That's like whenever you see logical paradoxes, what's your problem? It's like, oh, I got a logical paradox. It's like, I took the set of all sets, but it's its own power set, so it's smaller. It's like, well, why don't you try the reverse and just have it's not an ordinary set? It's like, oh, well, I already had an axiom that all sets have to be well-founded. And it's like, well, clearly they're not if when your quantifier is applied to it and makes an extraordinary set. Oh, well, what should I do about that? It's like, well, first you acknowledge that as the case, and then you acknowledge that the restriction of comprehension of the axiom of regularity that's called well-foundedness makes a limitation in that there are objects of mathematics outside of it that you must necessarily acknowledge exist in results. All right then, and what's the benefit of that is like then you're not entirely wrong in a world of logical paradox and fallacy. So this is one of these things that come into you can understand Cauchy's pain. He clearly could no longer uphold his definition without coming across as hypocritical and non-conscientious and lacking mathematical rigor. So that's an interesting story. Given that Fourier's examples were now interpreted as counterexamples, the puzzle was evident. How could a proven theorem be false or suffer exceptions? We have already discussed how people in the same period were puzzled by the exceptions to the Euler theorem despite the fact that it had been proved. So counterexamples are always, they're interesting things. And so it's like, you open up the counterexamples in topology book, and sometimes in the first one says there's the smallest real number or something like that. So it's like, whoa, how's this going to be? Oh, and now let's read the next section. Seidel's proof, S-E-I-D-E-L, Seidel's proof, and the proof-generated concept of uniform convergence. So there are lots of laws of convergence. There are lots of criterion of convergence. There's a strong and weak laws of continuity and convergence and large numbers and how induction is to carry and follow And then here it's framed in terms of the inductive impasse in the middle of nowhere, and the Borel versus combinatorics in the almost everywhere and almost none of Cantor space, and square Cantor space, the space of all sequences of zeros and ones, and whether or not those are arrayed in a square Cantor space, whether in order. And so here it's talking about uniform convergence. Everybody felt that this Cauchy-Fourier case was not just a harmless puzzle, but a fatal blemish on the whole of the new rigorous mathematics. Dirichlet, in his celebrated papers about Fourier series, while preoccupied with showing exactly how convergent series of continuous functions represent discontinuous functions, while obviously very much aware of the Cauchy version of the continuity principle, did not mention the obvious contradiction at all. Well, we can't read anything to why he did or didn't. I haven't really studied the man enough to guess as to his intentions or reasonings. Did not mention the obvious contradiction at all. It was left aside at least last to solve the riddle by spotting the guilty hidden lemma in Cauchy's proof. Where, as Cauchy had put it, the proof is based on an incorrigibly false assumption. See also Raymond. Wow. But this happened only in 1847. Why did it take so long? To answer this question, we shall have to look at Seidel's celebrated discovery a little more closely. So it seems that there's a certain privileged class of discoveries called celebrated, and that these are ones that then people figure are strong enough, even if they're hypocritical, that they'll hold up otherwise the proofs that people need to have left for them to prove the rest of their mathematics, while not allowing what are these exceptions, which still would make their own rules and be part of mathematics. And so they're celebrated in a sense by they solve a lot of interminable debate, because when these questions are open, then they're subject to all, not just the vagaries of definition and interpretation, but the vagaries of development, which are arbitrarily harder and worse. And so they could be celebrated because then they could go back to a nap, even though their wastebasket is on fire. So it's this kind of thing. So he says, let there be a sum of a continuous functions. It's convergent series. So let sigma fn x be a convergent series of continuous functions. For any n, find the series and the element of n at x equals the sum of m equals 0 to n of fmx. All right, so they range from 0 to n, and instead of usually that'd be 1 to n. And so he's saying that those would be the sum, and then Rnx equals the sum m equals n plus 1 to infinity of f sub nx, which would be I guess those must be in the terms, the f of m and x. So it's just only one convergent series, and so it's not accumulating. This is written in the sense that the series is it's a sequence that is summed, not a series that is sum. Usually we say a series would be a series that is a sum, but according to what he's defined as these, then you can only be referring to this, because otherwise it would be infinite quantity if it was non-zero. An infinite series of finite and non-vanishing elements. So these must be the differences that he's summing. Then the gist of the Cauchy's proof is the inference from the premise: given any epsilon greater than 0, there's a delta such that for any b, if absolute value b is less than delta, then s of x plus b minus s and n x plus b minus s and n x is less than epsilon, because there is such a delta because of the continuity of s n over x. See, this is just this simple one where there is a convergence criterion. If the difference between the nth element and the n plus 1th element is always small, the difference between it and the limit it attains to is always decreasing, strictly decreasing, and it goes to 0. That's basically this together. And 2, there is an n such that The absolute value or the magnitude of r sub n x is less than epsilon for all n greater than or equal to n. So this is the arbitrarily larger number. There is such an n because of the convergence, dot, dot, dot. And there's an n prime such that the absolute value or the magnitude of r n x plus b is less than epsilon for all n greater than n prime. There is such an n prime, dot, dot, dot. So this is kind of what I mentioned before about it. So this is so clearly proven. And then 3, dot, 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 to the conclusion that fx plus b minus fx equals sn x plus b plus rn x plus b minus s and x minus rn x is less than or equal to, it establishes an inequality. It's making so for a case for inference that it's always so, that it carries. S and x plus b minus s and x plus r and x plus r and x plus b is less than 3 epsilon for all beta less than delta. And then this reduces what's a constant to a constant. Now the global counterexample is provided by series of continuous functions which converge to Cauchy discontinuous functions. See, this is where we usually rather have our definition of function is just like it's a free function. And that if we want to be Cauchy functions, you call them Cauchy functions. And if you want to be, and functions are Cartesian, but if you want a function that's not Cartesian, you have to say non-Cartesian function, this kind of thing. In continuous functions. About then that what is differentiable is another class and dot, 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 and like so. Which converge to Cauchy discontinuous functions show that something is wrong with this roughly stated argument. But where's the guilty lemma? Well, slightly more careful proof analysis using the same symbols as before, but making explicit the functional dependencies of some of the quantities produces the following inference. Sn x sub b minus Sn x is less than epsilon, if b less than delta, epsilon xn. Rn x less than epsilon if n greater than n e epsilon comma x. Rn x plus b is less than epsilon if n greater than n epsilon x plus b. Therefore dot 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 is same. The hidden lemma is that this maximum max n epsilon z should exist for any fixed epsilon. This is what came to be called the requirement of uniform convergence. Well, I thought that was already kind of implied because of the existence of the third item there. There are probably 3 major impediments in the way of making this discovery. And so, what happens, and it seems like Seidel's first proof was kind of along the lines of like, this proof does not exclude Fourier's example. And the second one said, this proof includes Fourier's example. It's kind of like so. There are probably 3 major impediments in a way of making this discovery. The first was Cauchy's loose usage of infinitely small quantities. Algebraic and arithmetic. Algebraic and or arithmetic. Not necessarily both. Usually algebraic. Infinitely small. Vanishing, or as of an infinitude of them being finite, like iota values, standard infinitesimals. The second was that even if some mathematicians had noticed the assumption of the existence of a maximum of an infinite set of n's is involved in this proof, they had very well have made it without a second thought. Ooh. I don't think so. I'm not necessarily sure. So it would have been required to box it out. That it would necessarily, that there would be an arbitrarily large, not necessarily maximum, but just arbitrarily large, and that the maximum exists is under whether it's decreasing or strictly decreasing, but it's decreasing. And the difference is vanishing. They may very well have made it without a second thought. Existence proofs in maximum problems occur first in the Weierstrass school. Now, Weierstrass is held up as pretty much really sharp and rigorous and accurate. Weierstrass is kind of like, what do we call Cauchy mathematics, the convergence criterion? We call him Cauchy-Weierstrass. But the third and main obstacle was the prevalence of Euclidean mythology, this good and evil spirit of early 19th century mathematics. So here that's interesting about Euclidean methodology, because that's the only school that there was available at this time. This is where the analysis came up, and it was made into rigorous formal analysis of that. Just kind of like in the times of Euclid, that geometry is made rigorous and formal in its few and successful axioms, in its few and successful classical constructions. And so I'm not sure though exactly how that applied, because the ancient Greeks, when you include geometry, you also bring in all the rest of the schools of the ancient Greeks, and then you get into anything to do with the methods of exhaustion and Aristotle's and Archimedes and ... that they would be framed in those. And then that whether that was lacking in rigor was more along the lines of whether it was lacking in definition and exegesis and that kind of stuff. So he gets into stuff. Abel's exception barring method. Here, for example, Abel states the problem. He says that the domain of validity of the theorems, analysis in general, and that of the theorems about the continuity of the limit function in particular is restricted to power series. All the known exceptions to this basic continuity principle are in trigonometrical series, and so he proposed to withdraw analysis to within the safe boundaries of power series. See, that's fine. He just made an analytical region, but at the same time calling that all the objects of mathematics is hypocritical and asking too much. In a letter to Hounstein, dated 29th March 1826, Abel characterized miserable Eulerian induction as a method which leads to false and unfounded generalizations. And he asked what the reason is for such procedures have in fact led to so few calamities. His answer is, to my mind, the reason is that in analysis one is largely concerned with functions that can be represented by power series. As soon as other functions enter, and this happens but rarely, then induction does not work anymore, and an infinite number of incorrect theorems derive from the false conclusions, one leading to the others. I've investigated several of these, and I was lucky enough to solve the problem. Well, this is kind of that he's got a tool set, and he's pretty happy with it, and he's able to solve a lot of problems with it, and they all follow induction, because he doesn't have to exercise deduction, because that would involve knowing more than just the course of where he's at and his rule to figure out the next, and his more close milieu of framework of theorem. But then saying that that's not calamitous, or that miserable Eulerian induction is not induction. Basically he just says miserable Eulerian induction because he has a miserable Abelian induction. In Abel's paper, we find his famous theorem, which I claim stemmed from his grappling with the classical metaphysical principle of Leibniz in the following restricted form. If the series f alpha equals v0 plus v1 alpha plus v2 alpha squared plus ... vm alpha m plus ... So a power series in alpha with coefficients in v is convergent for a given value delta of alpha. It will also converge for every value smaller than delta, and for steadily decreasing values of beta, the function f alpha minus beta will approach the limit f alpha indefinitely, provided that alpha is smaller than or equal to delta. Now, for it to converge, as you might imagine, alpha is between 0 and 1, because otherwise there exists an arbitrarily small n that a to the n is arbitrarily large, and so and that there are no negative that there are larger ones in the positive terms, that the coefficients would grow unboundedly to otherwise result, because only the odd terms can have for negative, because there's only 0 and 1, which are all positive, and so only very particular coefficients are small enough, and that the powers get very, very much smaller, that like 1/10 to the 10th power is 0.901 or something like that it gets small enough. And when you only include the negative numbers, which can still stay close enough about 0 and 1 to have a finite convergent value. And this is why the power series are so great in convergence things, because you can contrive one that adds up to any convergent value, and you can just there's a simple one. It's exactly the same thing as the decimal representation if you look at it like that, or a number under a given finite bound, that for numbers between 0 and 1 you can so represent it in a space like so. When you think of the digits beyond the radix as just a coefficient in that base to the power of that integer power. So anyways, the first of all, the values are between 0 and 1. And then that is convergent for a given value of delta of alpha. It will also converge for every value smaller than delta. That's because it must be vanishing in these forms. And for steadily decreasing values of beta, as we would say, strictly decreasing, the function f alpha minus beta will approach the limit f alpha indefinitely, provided that alpha is smaller than or equal to delta. It seems that otherwise there would have to be like either in the either in the even or odd terms something that would make it so that it's possible to have a hysteresis, but still that then when you say that the limit goes to it in the limit, it still kind of would have the same kind of uniform convergence eventually. But it's framed a little bit differently, because the power series coefficient terms have that the greater contributions, you always figure that the greatest contributions are in the first initial segments of the terms, not that they're spread out all the way across, nor that they exist and grow in the later, the exact opposite is say, do you mean there could be a limit if all the initial terms are 0, but like somewhere that's arbitrarily large, that it's arbitrarily small, yet grows into the limit? Well, I've just defined such a thing, saying, well, in the space of all the power series, and all the power series you consider, as long as you only use the first 10 zillion elements in the coefficients for all the analytical character, and everything else under that is basically negligible, and you'd still be happy that's gone to the limit. It hasn't, but arbitrarily, that within that interval, according to interval arithmetic, you can make it so. Well, then the zillionth plus 1 can be just pop up. It can be just an indicator. It can be the delta's slid all that way. So this is just an example of the sorts of things to get into framing and boxing it. But here though, and then that's a pretty agreeable definition of this convergence of a result, about that if you have this power series and it's continuous in its domain and it's continuous in this function, that the convergence theorem applies to it, seemingly all right, because the hysteresis, or the intermediate terms, have for each one of them basically the same thing as the Seidel's arbitrarily larger delta epsilonics, that it makes it an inequality in less than m epsilon for any arbitrarily large m, because epsilon is arbitrarily smaller than delta. Modern rationalist historians of mathematics who consider the history of mathematics as a history of homogeneous growth of knowledge on the basis of unchanging methodology assume that anyone who discovers a global counterexample and proposes a new conjecture, which is not subject to refutation by the counterexample in question, has automatically discovered the corresponding hidden lemma and proof-generated concept. That's not so. People start with their idea fixed and they're like, I have an idea. I'm working in a different theory. We both attain to the same theory and the limit. I don't know why this limit result exists here that yours also does, but all the terms they're in inscrutable variables, or they're different, or one is arrived at via a means of approximation, and the other is arrived at as via some kind of closed form, or that this and that, this and this and other. So I would say that it's not so. But for somebody who's a historian of mathematics and is like, well, what's the history of mathematics? It's like the historian knows everything in mathematics. It's like, well, nobody knows all mathematics. It's like, if a historian of mathematics knows all mathematics, well, what does a historian of mathematics knows? It's like, whatever he knows, that's all is it. And I was like, what kind of historian of mathematics is that? It's like, well, there are better and worse ones. And so here we might say that the historian of mathematics might be able to pick up one of these two things and say, oh, well, I see you both attain to the limit, call it C for constant here, via method A and method B, and that either one of them is so, but without knowing the entire development of either or so, I can't really tell you which was hidden about the theorems and elements and as for either, unless I happen to already have a pretty thorough, fundamental, elementary mathematics already put together for all these objects of arithmetic and analysis and algebra and geometry and number theory and topology and sets and part theory and categories and functions and topoi and types, that I can rewrite A and B in all the different ways they can be fundamentally expressed in those ways and show how they're the same or different or where they vary. What's hidden to each other is not necessarily even existent in each other, but where they connect and describe the same things and model the same things, then they have those models of those objects and theories. That fundamentally for logic, then there's a model theory, which is a proof theory, and it's for extensionality and intentionality. So that's what model theory is for any given set of objects in mathematics, showing that a structure exists that one fulfills the other. One fulfills being the other, and anything you can say about one is so for the other. That's kind of how it is. For definitions, logical objects, axiomatic set theory, descriptive set theory. Here, this descriptive differential dynamics in definition. Modern rationalist historians of mathematics. In this way, such students of history attribute the discovery of uniform convergence to Abel. So in the authoritative Encyclopädie der Mathematischen Wissenschaften, Pringsheim says that Abel demonstrated the existence of the property today called uniform convergence. Hardy shares Pringsheim's views. In his paper, he says that the idea of uniform convergence is present implicitly in Abel's proof of his celebrated theorems. Bourbaki is even more explicitly false. According to him, and remember Bourbaki is a panel, Cauchy did not at first perceive the distinction between simple convergence and uniform convergence, and considered himself able to demonstrate that every convergent series of continuous functions has as its sum of continuous function. The error was almost as soon revealed by Abel, who proved at the same time that every complete series is continuous in the interior of its interval of convergence by the reasoning which has become classical and which uses essentially in this particular the idea of uniform convergence. It only remained to disentangle the latter in a general manner, which was done independently by Stokes and Seidel in 1847, 1848, and by Cauchy himself in 1853. So, as you can tell here, between Imre Lakatos, Abel, Pringsheim, Hardy, Bourbaki, and Cauchy, that sort of all over the map for an arbitrarily small region in France. Abel did not reveal Cauchy's mistake in identifying the two sorts of convergences. His proof does not employ the concept of uniform convergence any more than does Cauchy's. Abel's and Seidel's results are not in the relation of special and general. They are on quite different levels. They basically are just pasting over what's a vagary and what's a function. So function theory and the non-Cartesian functions, the classical functions, the continuous functions, the differentiable functions, the smooth functions, all these being smooth functions, the idea being that some of them are differentiable functions and some of those are differentiable functions that are non-zero and non-infinite, and that some of those otherwise plane curves have some that are otherwise just smooth functions. Has that any plane curve is a smooth function and vice versa for any function in two coordinates, but the classical functions are rather somewhat restricted. Then there are furthermore, and after that there are non-standard functions that are not necessarily having any discontinuity or gaps in them, like Dirac's delta, or there are those that have analytical character while being discrete, like the natural unit equivalency function and the iota values. Functions, in some of them continuous and some of them generally so, or especially so. Abel did not even notice that there's not the domain of eligible functions which has to be restricted, but rather the way they converge. In fact, for Abel, there is only one sort of convergence, the simple one, and the secret of the sham certainty of his proof lies in his caution and lucky zero definitions. As we now know, in the case of power series, simple convergence coincides with uniform convergence. Whilst I am criticizing the historians, I should just mention that the first counterexample to Cauchy's theorem has generally been attributed to Abel, that incursion Fourier was noticed only by Jourdain, but he, in the ahistorical spirit already noted, draws from this fact the consequence that Fourier, for whom Jourdain had a great admiration, came close to discovering the concept of uniform convergence. The point that a counterexample may have to fight for recognition, and when recognized it will still may not lead automatically to the hidden lemma, and thereby the proof-generated concept in question, has been missed by all historians so far. And this is where Jourdain was a great translator, as well as a historian of sort. Well, that's nice. You not often really see too much notion about like the back and forth and the vagaries and definition and the hypocrisies, you know. But anyways, hey, have a great day, and keep in mind that these days it's still that no historian knows all mathematics, but they do know what they know. And that you can have a fundamental theorem of mathematics with these theories I mentioned all these times, arithmetic, algebra, and all their little elementary objects, very, very simply. They go together, and there's even an extraordinary theory. There are no logical paradoxes. They've all been kind of resolved in these slates, and countability and uncountability put back together with these slates of the non-Cartesian function, natural unit equivalency function. It's pretty great. Quite modern. Well, all right. Hey, have a great day.